Hello everyone and welcome to Handmade Hero, the show we code a complete game live on stream. We are doing some character movement code right now and I'll be honest with you, I think we pretty much finished up our simple little example of how to make a hopping character yesterday, and so what we've got to do today is start talking a little bit more broadly about animation, because what we want to do now is we want to start to tune this animation so that it looks a lot more satisfying, right? And I'll show you just real briefly where we're at, just so you can understand what I'm saying if you don't remember from yesterday, or even if you do, just to sort of refresh your memory a little bit. Here is where we are at on Handmade Hero's little dude. We gotta do some OpenGL fixing one of these days so we don't have that texture download problem. So you can kind of see what we did is we made the little body hop along, and what I said yesterday is, well, now we have to do some stuff. We want the head to always be connected to the body. We want it to kind of stretch to meet where the head is, and we want to add more. Like, that's a very, in my opinion, very dry animation, very mechanical, right? It hops in a little parabola, but it's not very satisfying. It's just like I'm just literally moving the thing over. And so remember that, like, keep that in mind, what that looks like, because that's you'll want to sort of appreciate how we get from where we are there to where we are going to be after we sort of work on the animation a little bit more. So before I go any further down there, it's probably a good time to do some blackboarding so that people who don't know very much about animation will understand the sorts of stuff that we're trying to do here, and have some reasonable perspective on what is, what is really the way to think through these sorts of problems and animation in general in a game context. So I don't know how much programming we'll do today. It depends on how long it takes me to get through these concepts and how much detail I go into on them. I'm not sure how much is appropriate given what we've already done, but I feel like we haven't really talked about it too much. So let's start by just taking the sort of category a little bit broadly and talk about animation in general. So what do we actually mean when we're talking about animation? Well, obviously, we're starting from a very basic premise whenever we're talking about computer animation and computer animation for games, which is that we know we sort of have this like imaginary kind of film strip, that's kind of playing here, where we've got frame 0, frame 1, frame 2, frame 3, right? And here's, I'll draw in the little perforations down the side to make a good film strip. And so obviously, we can't really display anything quote-unquote animated. We're just displaying still frames, and those still frames are meant to appear to the user as if there was motion happening, right? And oftentimes we try to make it appear sort of like what would happen if you actually had a camera and were actually filming something. And the reason for that, of course, is because that's what people are used to seeing. They're used to watching a movie or a television program on a monitor like the one that we use for games. And so what we expect to see is that. Now, what we're trying to do when we produce these series of frames is we're trying to capture the effect of having something having moved. And what generally happens, right, if you imagine what's going on in terms of sort of the process we're simulating, right, there's a camera, and inside the camera, this film, this negative here, the negative that we're actually talking about is flowing through this camera, right? It's going through, and it's going into like a reel, right? So it's kind of like coming out here and going onto this reel, and it's capturing something on these frames. And what it's actually capturing depends quite a bit on how the camera is set up, right? Inside the camera, there's a little thing called a shutter or an aperture, and you've all seen it, right? It's the thing that like kind of looks like this sort of a thing. And it kind of spirals in to be a small shape, and then it widens out again, right? Right? It's like it can close all the way to nothing, and it can open up to a certain state, and it like based on how big this shutter is, more or less light gets through, blah 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 blah, right? Now, we're not going to talk about depth of field or all those other rendering things which we might care about with the aperture, because we're talking about animation right now, so we don't care about any of this other than the concept of exposure time. And what exposure time is inside a camera, right? You open up that aperture to like take light into the front of the camera and expose the film on the other end. And for the entire duration of that open period, photons are coming in through the camera and hitting the film and exposing it. And what that means is that a single frame of animation, right, is not technically an instant in time, right? It's not instantaneous. What it actually is it's a interval of time. Okay? And that interval is specifically, it is exactly however long that aperture was open for. Okay? When the aperture closes, the film stops being exposed and it advances. When the aperture is open, the film is getting exposed, and it's that amount of time that we're capturing. So if, for example, I was using a camera and I set the shutter speed to 1/60th of a second, then I know that I've got a 16.6 repeating millisecond exposure time, which means that there's essentially that much worth of photons coming in. Okay? So what that means in terms of actually, if we're really talking about animation in its broadest sense, right? If we're talking about, animation inside the computer in its broadest sense, what we actually want is to be able to capture an interval of time, right? So we actually aren't trying to find out, say, where an object is and only its instantaneous position at some point in time. We're actually talking about where did the object, if we're trying to draw that object, where did it move, right, during a particular interval, if that makes sense. So in the furthest forward part of the future, when we have infinite computing power and infinite technology, and I don't know where that, we're in Star Trek and everyone's got weird stuff on their forehead because they're an alien. And you go into the holodeck because the writers ran out of any ideas for the actual stuff to take place on the spaceship, so they're going to use virtual reality to simulate like Sherlock Holmes or something. And before that writer gets fired, and I hope to God they get fired, basically we're talking about there. What we would actually be doing when we're rendering imagery is we're talking about capturing what happens in that interval. And the reason why that's important is because if you look at pictures, and we talk about two frames. Here's frame 0, here's frame 1. And I've got like a ball and it's here, and then on another frame it's over here, right? Well, if I go to see a movie, that's only happening at 24 frames a second, but it still looks great, right? And if a game runs at 24 frames a second, well, maybe that doesn't look so great, depending on the game, right? It looks very staccato. And part of the reason for that is because when you're shooting a film, you get motion blur, right? And that motion blur is specifically because of what we're talking about. It's because it's capturing an interval. So if this thing is coming across the screen, you actually have this big, long, beautiful blur that's showing up there. And that blur is conveying all of this motion to your eye that makes it look a lot more rich. And so again, at the limit, what we're talking about when we're talking about animation in computer graphics, we're not actually talking about figuring out how to draw a single frame and then another single frame of time. We're talking about drawing an interval of time and then another interval of time. And that interval is proportional to what kind of a camera effect we were trying to simulate. Now, we're not that fortunate these days in computers, so a lot of times we can't really do that. And so sometimes we have approximate ways of approximating motion blur, but they're not really correct. And there's a bunch of corners we cut, and a lot of times we don't try to do motion blur at all. We just try to get a high frame rate, like 60 frames a second, and hope that things aren't moving so fast that they look ugly at that rate. But it certainly does lend a certain crispness to the images you will see in CG that doesn't have motion blur. It definitely looks different, right? Even at 60 frames a second, there would be motion blur on fast-moving things, especially the kind of things you see in games, fast cars moving around and bullets whizzing by and all these sorts of things. So that's important to understand. But assuming you understand that, now we get to what we're actually going to try to achieve in Handmade Hero, which is the simpler problem, which is just instantaneous. So if we assume that our frame rate's high enough that we don't care too much about motion blur, or that the certain things we might want motion blurred, we will hack, right? We're going to hack those in. Because, like maybe I swing my sword and it has this little blur trail on it. Well, okay, we'll hack that in. But we're not going to try to have necessarily a robust solution for that where everything is always motion blurred correctly all the time. Then we get down to the sort of thing that we're actually doing right now, and that's what we will mostly be doing for Handmade Hero, which is the instantaneous problem. But it's important to understand that this is a hack, right? Doing things instantaneous is as if you had an infinitely fast shutter, so that it opened and closed in just a split second of time. And of course, in the real world, you can't even do that because there aren't enough photons in an instant. No, photons have a speed. If something opened and closed in a literally instantaneous amount of time, the film wouldn't get exposed because no photons would go through the aperture, right? So inherently, there isn't even a real world analog to what this is. The closest thing I guess you could say is, imagine you had a strobe light and you could somehow only get the first bounce of the strobe light, and you like shot it and like captured just those photons. I mean, I don't even know. If you could strobe all the lights in the world and get them to arrive at the I don't think there's any way. I can't even make up a situation in the real world that would actually produce a reasonable, like a real world image, like I'm looking out at the world, and that actually obeyed what we're talking about here. So this is definitely a hack, but it's a hack that's totally fine. Things often don't move so fast, they need much motion blur. And like I said, you can always hack in some motion blur over the top of things for things where you find that it's important, and that's not so bad. There's also ways of using the velocity of objects to do a post-pass motion blur, for example, where you can motion blur everything, and it's just not accurate. It doesn't handle like curved motion and stuff like that, right? Things always appear to be moving somewhat linearly. But again, if the frame rate's high enough, not so bad. So we have plenty of techniques at our disposal we can use later if we're too worried about that. So I don't want you to think it's a super bad limitation that we don't get to do this in games. We have plenty of techniques at our disposal that can compensate for some of this stuff. But on the whole, is it a hack to do the instantaneous thing? Absolutely. And so it's worth understanding that because later on in your graphics career or whatever you're doing, it's important to always have that figure in mind, because you're wondering, like, why can't I capture this effect, or what do I need to make this look better? And you want to understand that fact that in the real world, you're getting motion over time is accumulating onto the film, and that's what you're actually going to see if you go to see a movie or anything like that. So instantaneous animation is about being able to take some sort of a function, sample it at a time, right? And we want to produce, like, it's essentially a state of the world, right? So we want to be able to render the world, and we want to be able to render it at a time. And the way that we, you could imagine we have some function, we pass in, here's the time that we want to take a look at everything. It tells us where everything in the world is, and then we're just going to add, the next time around, this is t0. T1 is going to be equal to t0 plus, our time step, which is 1/60th of a second. We move it forwards, and we keep going, right? And then we take it at time t1. Okay, so that's essentially what we're trying to do with animation. And the important thing to know here is that usually in games, we want the flexibility to sample these functions at arbitrary t. Meaning we don't just want something that's like f of 0 is something, and f of 1 is something, and f of 2. Like, we don't want to have a discrete step. That was how old games work. In the old days, when you had an arcade game or something like that, it was locked to 60 hertz on the gun, the CRT or something like this, and it would literally just update 1/60th of a second. Everything was hard-coded in what happened in that 60th of a second, and you got that. You were talking about literally a discrete thing here. And that makes sense when you don't have floating point, when you don't have a lot of computing power. We have that now. And so what we'd rather do is have the ability to adapt a little bit. And the reason for that is we run on multiple types of hardware, okay? We don't know that our frame rate is 160. It might be 1/50th of a second. It might be PAL, right, or something. It might be 1/30th of a second because the user's machine is too slow. It can't handle 60 frames a second. But we still want to run because it's okay. The game can be playable at 30, right? Maybe the user's super crazy about frame rate. They wanted it 1/120th of a second, right? They want 120 frames a second. So typically, again, we want to be able to sample it as a t, and we want to be able to plug in anything here. So we want to be able to advance our time step in any kind of floating point increment we might want, okay? And alternative to that, you might do it. You could do an alternative structure of your system, where you had some fundamental quantity that you never went below, like let's say 1/30th of a second is your fundamental quantity, you could then do it in a discrete way like this, and you just say, well, if I want 120 frames a second, I just do 4 of these, right? So you can, there are other ways, I'm sorry, other way around. If I pick 1/20th of a second and I want 1/30th of a second, I do 4 of these, right? And then I could do something this way. But in general, you know, the trend in games most of the time is to have that system be flexible so you can call it with whatever you want. And you want to keep it within a certain boundary, so you don't call it with 6 hours between frames, and you don't call it with 0.000001 nanoseconds in between frames, because it'll fall apart and the floating point accuracy will just, you know, explode at that point. But assuming you're within a reasonable range, 1/15th of a second to 1/600th of a second, let's say, you're okay. So that's really what we're talking about here. And so what that means is, you know, do we have a single function that produces the state of the world? Well, in a sense, we sort of do, right? We have like game update and render, but really the actual math functional part of this, the things we're actually talking about now, what we really have is that giant, you know, world function that says what's the world look like at this point in time, is really typically composed of lots of tiny functions, right? Like maybe I've got the function here that moves the hero, right? And maybe I've got the function here that does the head bob, right? And maybe I've got this one. So, you know, you've seen this in the code when we're going to update the world. We have lots and lots of ways of creating these functions over time. Some of them are explicit, like that hopping spline we had, right? Remember that one? That was an explicit function. We actually have in the code, in fact, if I go here to world mode, right? Here is that actual explicit function, right? There's a function just written out exactly that takes in t, whatever that t value is, 0 to 1, and produces out that, that value that is the location, right? Some of it that way. Other ones, like move entity, right? They don't have a way of producing an absolute position. What they actually do is take one position and a delta and can update, right? So they are essentially computing only the first derivative of the function at that time, okay? And so it's important to understand there's kind of 2 ways of doing. There's 2 types of functions that we already have, and this is very common, right? We have functions that allow you to do a function at time and output the exact position at that time, and you can plug in anything you want here. That's like our jump. And then we have other ones that require you to tell it what was the previous position. So this is an input. I need to know where I was, okay? And then what they will compute is not this. This is not possible. What they will compute instead is what's the first derivative of the function at that point. They will multiply it by the time step, and that will produce the new p, okay? And this, by the way, we were talking about Euler in the pre-stream. This is a forward Euler step. This is basically saying I have a place I'm at, I have a derivative, and I want to multiply the derivative by the time step to get to my new location, okay? This is numerical integration. It's really, really crappy numerical integration. And for most things in games, it's actually fine. Because if you don't have any kind of weird physics going on, you don't care, right? But that's what we have to do, and the reason that we have to do that is, again, like I said, that function, there is no function for the position of the guy. We're moving the stick around, changing his acceleration all the time. He's bumping into things. So there are all these discrete things that are changing. So there's no way to write this. Whereas with that hop, well, the hop, we know when the hop starts to when the hop ends, it's that exact curve. We don't have to do any kind of that updating. We can evaluate directly. These are always these nice, super accurate, beautiful things. When you can get away with writing an explicit thing for an animation, you're loving life. It's great. But just a lot of things we want to do in games just realistically aren't that. And even these, like you saw, it's not like it's the whole guy's trajectory that's that way. It's only like for one hop, and then we've got to do other discrete business to sort of line it up, right? And that brings me to the other thing that I wanted to say, which is that the f of t notation, right? Like this is the f of t and this produces the world for us. Well, this is not really true either. Typically what happens is this t, there's lots of little t's that actually are in here. There's the t of the bobbing of the head, there's the t of the hopping, right? And all of these are sort of these sub little time values that we create to do these little parts of animation, which all get evaluated separately and in our code, and then they sort of all put out some position that gets fed up eventually into the state of the world, right? So this would be, it'd be great if we magically had some function for the whole world and it would just put in a t and out pops everything and it's all analytical and direct. Great. But that's not the reality of it. So typically what ends up happening when we talk about animation is we talk about lots of functions, of lots of t's, right? Lots of different t values. And those t values have very different ranges and all sorts of stuff. And so what we do is everything tends to be driven off that big delta t. Like this f of t, like I said, it doesn't really exist. Instead, what happens is we typically take, okay, we know what was the time last frame, we know what the time is this frame, right? We know how much time has elapsed, it's the delta t. So what we do is we feed that delta t down to everybody. And then all these little time values all throughout the program are all getting updated by that t, and all outputting the positions that they need to. Some of them are, like I said, literally doing that. They're literally taking t hop and adding delta t to it to produce the new location of the guy. They feed that t into an equation of it, right? F hop of t hop, right? And that out comes the position of the hop, right? So that's happening. But then other times that delta t is used in a sort of an Euler step where we don't know. We save the old location of the guy, we know his velocity, or we try to compute it, we move him by that amount, and that's his new location. Again, an Euler step there. It's not analytic, it's not directly computed. Okay. And so typically, even though they're all the same kind of unified concept at a high enough level, we typically call this physics and this animation. That's just what they typically end up getting called. When you have a function of time that evaluates the state of something, and you can just put in the t and out comes the state, we typically call that animation. We call that animating a character, or that's the animation of this character, right? When we put in just a delta t and we try to solve for where this thing might have ended up with a bunch of stuff that happened, that is what we call physics. They are both actually just animation, or they are both actually just physics, depending on what you want to call them, right? They both move a physical thing in some way, right? According to some rules. But we tend to use those two terms in that way in code bases. And so, it's intuitive. It makes sense, right? Because this is a thing that seems to be doing movement kind of like physically based or whatever. And this is the kind of thing that's like, oh, I had the artist like made some keyframes and I'm moving between them, right? Okay. So what we're talking about now when I say animation then at that point is we're talking about the f of t kind of thing. And we're sort of talking about, well, if I want to do one of these f of t kinds of things, what are sort of the techniques that are involved for doing these f of t's, where I get sort of stuff out. And you saw one of them, which was that parabolic arc, right? B-splines are a very common one of these, right? A B-spline, like you've seen many times before, are what like animation packages use. For example, if I want to do an f of t equals some like animation curve, right? Like I want like a curve in space somewhere, right? And I author these little B-spline handles that kind of go through here, you know what I mean? And then I just say, as my t goes upwards, it moves along the path of the B-splines, right? And that's how I animate a dude. Similarly, you might even see Euler angles in there for joints, right? Because I want to be able to say, like, oh, I don't know, I've got sort of this joint here, and I've got this maybe it's, let's draw the shoulder of a guy. Let's say here's his shoulder coming out here, here's his head up here, and whatever. And I just want to talk about like the animating a curve for the rotation of this thing, right? So maybe I make a B-spline, but the B-spline is talking about the angle of this joint, right? Blah, 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 blah. So B-splines are kind of the workhorse of animation very typically, and we almost did something like that before with our parabola, because a parabola, obviously, a second order B-spline is a parabola, right? First order is a line, second order, this is first order B-spline is a line, second order is a parabola, third order is a cubic, right? So you're talking about, in fact, let me draw these for you, in case so 0th order. Let's just talk about B-splines for just one quick second. These are the things you see in all the, all your animation packages. Let's put this a little lower. Here's the order of my B-spline. 0th order is a step function. It's basically teleportation, right? So I'm here, and then I'm instantly here. I'm here at 0, I'm here at 1, right? I'm here also at 0.4, I'm here also at 0.499999, and then when I'm at 0.5, I'm over here or something, right? Depending on how I want to sample it, obviously. But in general, I literally teleport from one to the other in a 0th order B-spline. A first order B-spline is a line. A first order B-spline is something that does a standard lerp from one to the other. At 0, I'm here. At 0.5, I'm here. At 1, I'm here. At 0.25, I'm here. 0.75, I'm here. Right? Second order B-spline is a parabola. I've got one more point to specify, like so. In fact, you know what? If I'm sampling these the same way, you would actually be here all the way up to 0.99999. If I'm sampling them the same way I'm sampling here. It would only be once you get to 1 that you go to the next B-spline key, which is here, right? This is actually another key, and that's kind of important to mention. These are stacked on top of each other, right? You know how you make these in an art package, right? You kind of put one down. I'll put my third here. You know how you make these in an art package, right? You put one here, you got 2 handles, and it kind of does this sort of thing. Right? And here's 0.0, 1, 2, here's 3, here's, then here's 4, 5, 6, right? And so these are like the keyframes, and these are the tangent handles, quote unquote. You know what I'm saying? So if I was to do that, these are the keyframes. Here's keyframe 1, here's keyframe, here's keyframe 0, here's keyframe 1, here's keyframe 2. Well, here's keyframe 0, and here's keyframe 1 over here. The actual endpoint of the spline is going to be over here as well, right? So this guy is actually taking this as the sample point now. So in a parabola, the big difference now when we get to second order, which is why it's the first one you tend to see in animation at all, is because now there's actually a point that is not at either keyframe, right? We have where we're starting and where we're going from, but we also have an in-between point, right? And so what we end up drawing doesn't ever touch that point. It's kind of like this sort of a thing. Right? And then finally, for third order, we have cubics, which means we can specify 2 points, which means we can actually have a wiggle in there, right? So we can have this sort of a thing. It can actually change direction twice. Yeah. So anyway, we'll talk about B-splines a little bit more completely later, but I just wanted to kind of get that out there, the different, while it was kind of something that was coming up. So B-splines are a very common one of these, right, because they're very versatile and you can kind of make anything you want with some kind of a B-spline. And these degenerate nicely. You can always evaluate a cubic if you want. Your whole program could evaluate cubics if you want to. And just by what's called not doubling, which is just repeating values multiple times inside the same cubic, you can drop it down to any one of these. So an animation system built strictly on cubics can actually do parabolas, lines, and step functions without actually doing anything else. It'll just automatically work, which is kind of nice. So that's kind of a neither here nor there. So anyway, that's one of those very versatile functions. But just because this is what all animation programs are always using, that's because it's a nice general tool that they can give animators, and then they can make all sorts of stuff by tuning what the curves are, and they're fairly intuitive because people grabbing these handles and moving the curve around, so they seem to be able to do a reasonable job with that. So great. Good job, everyone, B-splines. But there is nothing special about B-splines. Animation is literally just that f of t. It's the f of t that produces the state that we want, and that could be formulated as a B-spline. It could be formulated as any function we want. Any function at all. And you saw me do that yesterday. Instead of starting with a B-spline, I just said, I want a parabola. Here's the constraints on my parabola. Let me solve for what it's going to be, and out it popped. I didn't have to start with the B-spline formulation. I can get a second order equation a different way if I want to, right? So the important thing to remember about animation style stuff is just we are trying to make functions of t. We can make them any way that we want. If we don't know what to do, or we're confused, or we just want something artistic, yes, we can just throw a B-spline in there, and that, you tune it, tune those handles, do whatever, that will work. But we can also be more experimental, we can be more investigative, and we can generate any sorts of other functions that we want, as long as they are, feeding the t and out comes the state. That is the nature of animation, and that's where we're at, right? So, let's talk about what we mean by the state part of this, now that we know what we're kind of talking about with the f of t. Because saying B-spline or saying whatever, well, that's just like arbitrary scalar values in space or something like that. It doesn't really mean anything until we actually talk about what the kinds of state are that we're trying to generate. Now, obviously, we can generate any kind of state that we want, so we're free to do whatever we want there, but the question is, in games, what kind of states are we usually concerned with? How do we tend to model the things that we're going to be animating? And usually the way that we do this is we have some kind of preconceived notion, like, people ask me on the stream all the time, like, are we going to have like a skeletal animation system or stuff like this? It's like, that is all just sort of like a buzzwordy nonsense thing. Don't think about that. Do not think about those things at all. Those are just like specific instances of how things get animated. What you want to think of instead is you want to think of just parameter spaces. And all of the other ways that you might actually end up doing something are all just a way of sort of saying we're just going to use a parameter space that looks like this. If I say I'm going to do a skeletal animation system, it means I pre-decided that the kinds of state spaces I was going to handle look like this, right? So let's talk about those. Let's talk about the parameters of the state, right? Or the state vector. I could also throw in a physics term here for you, which is generalized coordinates. Wow. Handwriting, not my strong suit on the Wacom tablet. Okay. So what we want to think about is this f of t produces a state, and that state is something, it's anything, right, that we want to represent the world in a way we can render. Okay? Now, what that means is we are free to pick the set of parameters that make sense to us. And they could be anything, right? Now, you've sort of seen me do that to a certain extent before, right? I already have a situation where I talk about the ground point of a guy and the head height, right? And when I go and compute what this is, the head height of the guy is a function of t. It was f of t, that bob value, right, produces the height of the guy. The ground point, on the other hand, was f of t0 plus delta t times f of, derivative of f at t0, right? The ground point was physically simulated. The head height was animated. And there's my guy, right? Well, actually, I think he didn't have a body, right? He's just a head floating there, right? What is this system that I've created? Is it a skeletal animation system? No. There's no skeleton, there's no bones, there's no nothing related to skeletal animation. And if you wanted to create this in a skeletal animation, actually you couldn't. The reason that you couldn't is because there's no such thing as head height in a skeletal animation system. What you would have to do instead, right, is you would have to create a bone which actually has 3 degrees of freedom, x, y, and z, right, or however many, at very least 2. And then you would have to go ahead and animate that y position of the bone as if it was the head height, right? Now, like I've said, you can certainly construct the same effect in a skeletal animation system. Can you create this? No, because this bakes in knowledge of the system. The code knows it does not need to simulate a bone for the displacement of the head off of the ground point. And the reason it knows that is because it knows it can only be displaced upwards. So it only has to compute one scalar value, right? So if we were to talk about the state vector of this system, the state vector of this system is a 4 vector, right? It's the ground point x, the ground point y, the ground point z, and the head height. Okay? So this is the state of the familiar. It's a state vector. It has 4 components, and that's what they are. Our job, when we simulate the familiar, right, is to take an f of t0, that's this, and produce the f of t1, you know, the new one, that's a new one of these. And the way that we chose to do that is by simulating this part with forward Euler, that's how it moved around, and simulating this part with a sine function, right? It was sine of t-bob or something like that, right? And that is the nature of animation code. You have a state vector. The state vector is describing the minimum potentially, or it could be fatty, but at least it must describe the minimum number of state variables necessary to go from nothing to the placement of all of the renderable objects, right? And that's what this does. Once I know these, I can produce the rendering output for this guy. Okay? So that's what we really need. And to be honest, we could talk about this, you know, let me be more explicit with my nomenclature, because I'm being a little sloppy here. That's not really what that is. This is actually the position vector, right? You could say. Okay? This is actually the vector of that I need to reproduce my drawing. You could argue that the state vector, if we're really being sort of pedantic here, is actually the gx, gy, gz, yes, but then t-bob. That's the actual state that I'm retaining, right? So you could say I've got this is the state vector, I simulate this vector forwards, then I produce this from it, right? Which is just a copy in the case of these, but it's actually a sine function evaluation in case of this, right? So I update my state vector forward using my delta time. That's a sine function. I'm sorry, that's just an addition here. It's a simulation step here. I then produce this position vector, which is a sine evaluation here and a copy for these guys. And then I have the information I need to do my render. Okay? So I don't really know how we want to name these. I'd have to look at the robotics literature to refresh my memory. But those are the two important concepts to have. I feel like we would probably call this our state vector. But, you know, we could call this our generalized coordinate vector, because that's what these are. They're the coordinates that describe this guy. And then we could call this our state, you know, our state vector. I don't know. But I feel like it's been 20 years since I read the robotics literature, so I don't remember well enough. But point being, these are the two things that you need to be concerned about in the system. And so if I was to draw it out, how this works, we have the stuff that is stored, okay? And that is, for example, like I said, it's the gx, gy, gz of the ground point and the t-bob. We have the stuff that's stored. We have then the sort of like render. We have the like render input here. And that's, again, the gx, gy, gz, and the and the height, head height, h head, maybe? I don't know what we want to call it. It's probably more like h. Handmade hero. We have the render input, and then the render input finally goes through one more process to produce our list of our sprite list, right? And these we have one thing, which is just the head. You know, we just have the head record, and what actually happens is we take these and we add this. So we take that g vector and we actually add the head height times basically a fixed vector that we know, which is like 0, 0, 1, which is like z value upwards, right? Does that make sense? So this is this is how animation works. You decide what your parameters are that you're storing that drive the animation. You have a way of generating some set of values from them, which are then used to compute the sort of whole state of whatever the thing is that you're trying to create and render. So it's typically this multi-step process. Now, if I say I want a skeletal animation system, all I'm talking about is essentially regularizing, I'm talking about essentially putting this part on, or I guess maybe not this part. We could say this part, really, at a minimum. We're talking about basically taking a Procrustes approach to this. We're basically saying from now on the render, the actual state that we're going to create is not going to be some arbitrary thing and then have a function that we wrote that can produce the final rendered position of the sprites. Instead, what we're going to do is say that everything always is the exact same, right? We're going to say that we have a concept of a bone, and a bone has particular information on it, right? It's got a displacement, like it's got a tx, a ty, and a tz, right? It's got a rotation in 2D. That's just going to be, a rotation theta. It's just going to be one value, rotation around the z-axis, you might say. And then it's going to have potentially a scale, right? And we're just going to say that everything has these values, and if you needed more than these values, you have to stick more than one bone on there. And if you needed less than these values, well, tough. We're just going to keep storing them anyway, right? And that's a totally fine decision, right? It's if you want to try and make that system more sort of streamlined and simple, then that's something you can do. But I often find it to be overly limiting, especially in 2D, because usually I want to do stuff like use crazy functions that operate on certain parts of this, and I don't really want to have to deal with getting at it some backwards way. Like, I have the way I want this sprite created, and I don't want to have to worry about fitting that into this preconceived notion of a bone. But again, a bone is just saying that, well, whatever this is, it's just going to be an array of these. That's it. That's all you get. So it better be that, because that's what it's actually going to be, right? Okay. So yeah. So at this point, I guess we've got about 10, 15 minutes later or something like that. I'm not sure. At this point, hopefully that all makes a reasonable amount of sense to you, and we're already doing it, so hopefully you should kind of be familiar with how that's going. At this point, we now have to kind of talk about that step where we actually do the rendering, because there's some stuff that we need to do there. So if we talk about our actual Handmade hero and how that's working and how I want it to work, we can sort of start to talk about how we're going to improve things. So for example, let's say that I've got that parabolic arc here, okay? And we've got that parabolic arc, and the guy is jumping along it. So here he is. He's got like a torso here, and he's got he's got like a cape, and that's just moving like this. And you know what? I guess let's not talk about the rendering. We'll talk about the rendering. We'll talk about the rendering tomorrow. Since I talked all about the functions and the breakdowns of the functions, we'll talk about the rendering tomorrow. And maybe I'll actually go do a little bit of code in the last 10 minutes just to sort of show how this sort of stuff works. So what I did, right, is I showed you guys how to write a function that was f of t that produces this parabola, right? So we did this kind of a thing. And it looks okay, right? It's not awful. Certainly I've played a lot of indie games with animation that's about that quality. But we want to do a lot better than that, right? We want to look good. We want this to look professional quality. We don't want it just like, okay, it's sort of moved and whatever. And so if we look at what's happening here, I would like there to be, the traditional principles of animation are they have anticipation and follow through. By the way, I should say, if this is separate, but every programmer who works on animation should have if you haven't read this book, don't work on animation. Like, you should read this book cover to cover before you do any animation work whatsoever. There's no question about that. So just like, that goes without saying, because otherwise you just won't understand what your goals are. I'm not going to try and cover the concepts behind how to conceptualize actual animation, because, like I said, that's like this huge topic that's about art and all that stuff. But you should at least take some time to familiar yourself with that if you're going to work on animation as a programmer, to say the least. I'm just going to say the terms and then show how I'm going to do them. I'm not going to try and motivate them by saying, well, in 1945, they decided to do blah and whatever or something. And that's how they figured out that this was important. Animation and follow-through are what I was going to talk about. Anticipation and follow-through is what I'm going to talk about here, which is that right now what happens is there's no ease in or ease out. We just immediately go on this parabolic arc, right? And when we land, we stop immediately. So it's just a perfectly like continuous linear motion. And a little bit of that is correct. Once a body enters a ballistic phase, it doesn't speed up or slow down, other than the gravitational part, right? So that's actually somewhat correct. Once I jump in the air, there's not a lot of deceleration or acceleration that's happening other than my gravitational arc. So that's okay. What's not okay is, how did I get this upward velocity, right? Well, if you've ever seen someone jump, again, there's the anticipation part of the animation of a jump. It's what happens in real life. I have to kind of come down and compress my body like a spring, and then I leap up into the air, and I use that upward momentum to lift me off of the ground. And so if you look at what our animation is doing right now, right, it doesn't look like that, right? It just kind of moves in that arc, and it doesn't feel, it doesn't have any feel of that sort of anticipation. So how do we take an f of t that produces a parabola and produce something that has a little bit of anticipation in it, right? How would I do that? Well, what I want to first talk about is how to produce a subsection of my time step, because this is, or of my time window, because this is a crucial part of how you code custom sort of animations, stuff like this. We know that the f of t for our parabola goes from t equals 0 to t equals 1. What that means is during my jump, it will start here at t equals 0 and end here at t equals 1, and that's all. So if I want to have more time at the beginning of the parabolic arc to do some anticipatory animation of coming down and coming back up, right? Well, I've got to do something about this problem. I've got to do something about the fact that, well, at t equals 0, I'm here. At t equals anything other than 0, I've already started my arc. I want to peg the guy at t equals 0 for at least, 0.1 seconds or something, or 0.1 of t, right? From 0 to 0.1 or something like that. I need a little bit of room there. So if I'm going to do that, what I want to do is I want to partition my window of t. And how do I do that? Okay. Well, what I do is I do a map into range. We've done this before. We've seen this before, actually, and we actually I think we even have a function for it, right? And we want to do a map into range normalized. Okay. Because what we want to do is say, well, we've got an entire t. The t goes from 0 to 1. And we want to start breaking it up into discrete pieces. We want to do anticipation, ballistic, and follow through. Colloquially, this is like this is the launch, and this is the land, right? So what I need to do is have some t values here. This is t like jump, and this is t, land or something like that. And what I want to do is now produce 3 separate t values. I want a t value in here that ranges from 0 to 1. I want a t value in here that ranges from 0 to 1. And I want a t value in here that ranges from 0 to 1. Right? And so what I need to do is take a t that's on my large t timeline, right? And maybe, in here, this is 0.3. And what I want to do is to go from there to producing what's this value right here, which is actually inside this t range, is 0.15 or something, right? And by the way, I want to know which of these phases I'm in. I want to know if I'm in phase 0, phase 1, or phase 2, right? I want to know which of these ones I'm in. So I want to partition my range, and I want to get out a value inside that range, right? And so let's take a look at how I might do that. Oh, well, that was good. I accidentally shut off my monitor. Shutting off my monitor is probably not the best thing to do if I want to do that, because I need to be able to see my code in order to actually make it work. All right, so let's open up Fored. And oops, that's not what I wanted. There we go. And I'm going to open up world mode, and I'm going to go ahead and jump forward to that parabolic arc part. So here you can see it. And if we go to our math routines, you can see that we've got a clamped version of this, and it does the normalization as well. So like I said, we already did this. We basically say, here's the minimum value, here's the maximum value, here's the t. Produce a new thing in that range and clamp it for me, right? So that's what we're doing. I'm just going to code it explicitly. In the future, we may want to make an actual system that facilitates this sort of thing, but for the moment, I'm just going to write it out. So if we are hopping, I guess if I want to do my movement t at the beginning here, it depends when we want to update this movement. I may want to update after the fact. In fact, I think I probably do. Go ahead and clamp that out as well. So what I want to do now is I want to test my t value as I come through it, and I want to see, okay, if my t value is less than whatever my my t jump variable is, which is when I want to leave, then I'm in my jump phase. Okay. If it's less than my t land, then I'm in my ballistic phase, and otherwise, then I'm in my my landing phase, right? So we know what we're doing in our parabola case. We know that we're just doing this. I guess we know we're also always setting the dp to 0 because we don't care about that either. But I know when I'm in my ballistic phase that I'm doing this. And so the only thing I have to do in this case is I have to modify my t value. So I can just say, well, give me my clamped t value. I want you to map it between t jump and t land. And then I can set t jump equal to like that, and I can set t land equal to that, basically 0.2 on either side or something. And now I've done my my windowing. So now if I go and look at the jump, off it goes. That's pretty funny. Although I think that's wrong because it looks like we're not actually, that doesn't seem like it's properly finishing the arc there, which I guess actually, now I think about it, is actually correct, because given how fast the person's jumping, if we're less than, in here, since I'm not setting it, when we get to here, I do have to make sure that we actually put ourselves down on the final location, if that makes sense. Because, remember, we're not ever evaluating it at actually t-land. We skip over t-land and get into that range as we're incrementing. So we actually do need to still, I don't know why I restarted this. But so there we go, right? And now it's just that windowing is happening, but I'm not doing anything inside those other windows. However, if I want to, I certainly can, right? I can certainly do some more interesting stuff here. And let's think about, for a second, what that would be. Now, we don't, at the moment, have any concept of the height of the, what's the word I'm looking for? That cape. There we go. We don't have any concept of how high the cape is off of the body, right? We don't actually know what that is. And so what I kind of want to do is say, well, okay, I'll just use maybe the t-bob value here to control that. So what I want to do is I want to do a clamp map to range on this, this initial jump phase. I want to take it there. and I'm going to say that the t-bob is going to kind of go, I want it to kind of come down and then back up again, right? So what I want it to do is I want it to sort of do almost a sine pattern, right? I want to do like that kind of a thing. And I don't really know exactly what I want that to look like because I haven't thought about it yet, but we can sort of play with that a little bit more. So I'm going to say that we'll set the entity t-bob. And you know what? Normally, I guess we want the entity t-bob in any case. We'll just cold set it up here to something like 0. And then I want that entity t-bob to be some parameter that I can use to drive that displacement. So the t-bob in this case, I'll just say that, well, you know, sine, if you think about what sine does, right? Here's our unit circle, right? So cosine of 0 is 1, and sine of 0 is 0. And it goes up to 1 over this arc. So if I wanted to capture this arc of going from 0 back to 0 as a sine, right, I would just say sine of my t value, but this is pi radians, right? Or half tau, depending on how you want to do it, right? So t times pi is actually going to mean, from if t ranges from 0 to 1, that will give me that sort of a bob. It'll go from 0 to 1 to back to 0. So I'm gonna use that. I'm gonna use the fact that we have that ability to go ahead and set the t-bob value to be t times pi, and then I've got that jump that I was looking for, right? That sort of springiness. So all I have to do now is when I actually draw this hero body, all I have to do is actually use that t-bob now. And I guess I don't really know exactly. We probably want it to go upwards, so I should probably say like, oh, okay, you know, this is actually going to be, you know, entity t-bob, and I probably don't want to move it. Well, we'll just let that be in regular coordinates, I suppose. And so when I come up here and I'm going to adjust this guy, we can say that I'm moving him down, right? And I probably don't want to move him down too much. We'll see how that goes. Did I set the right thing? I set the wrong thing. I wanted cape. There we go. And the other thing that we should probably do is, as we start to work on this, I'm going to slow it down quite a bit so that I can see what's happening, because that'll make it easier for us to debug. It's going so fast right now, I can't even really see what's going on, which, you know, doesn't help. So here, when we do our update, I'm going to go ahead and slow it down 6x from where it was. So you can already kind of see that we got to sort it. So we want the cape on top, by the way, and I should make sure that that's happening as well, so you can kind of see it. I'm almost out of time, so. So here's our t-bob of this dude, and yeah, at the moment, do we get to pass a sort bias into this thing? I don't really remember. We shouldn't have had to. Most of the problem with this is just that our art assets are stacked on top of each other, unfortunately, and I wish they weren't, because I would rather it be displaced upward. I'll just put this in here for now, but that will come back to bite us in a second, unfortunately. So do you see how that sort of adds this little bit of niceness to it already, even though we haven't done anything much at all? Just having that little bit makes it look more like it's jumping. Now, unfortunately, it's not quite what I would want, because there should be some continuation of that motion. So when I'm in the t-jump range, actually what I want to do is set this t-bob to be a little bit... I want this to be a little bit more... I'm trying to think of what I'm trying to say here. I want it to carry through, so I kind of want all of these things to sort of be active at the same time, in some sense. So what I really want to say here is I kind of want to say if t is you know, less than t mid or something like this. And I'm not sure what I want to tune that to be. But I really want to say is if t is less than t mid, then I'm going to do this thing, right? And I want it to be able to overlap. And what I'm going to do is I'm going to let it come down, come back up, and then come back down again. So it has a full range. So I'm going to actually let it go for all of tau, and I'm going to let that jump happen. Oh, but you know what I'm not going to do? I am got to make sure this t is right. Okay, I'm after t jump and t land. So that should clamp properly to 0, which means we should stay at movement from I feel like that should have been right, actually. I'm not sure why it wasn't. Am I mapping this wrong? T jump to T land. Ah, right. I forgot. I can't overwrite my T like that, right? So this actually has to be this sort of thing. I was taking advantage of the else-ness of it all, but you can't do that, right? If I'm going to clamp these values and if I'm going to let them overlap, I'm not allowed to do that anymore. And so, do you see how that kind of looks a lot more like a jump now already, even though we haven't really done much to it? Just having that happen is just much nicer, right? And so similarly, what I can do now on the landing is do exactly the same thing. I can sort of carry that through where I take the same procedure we did here, and this time we're just going to play it from that T land all the way out till the end, like so. And so, again, really straightforward. Nothing particularly crazy there. But now it just gives us like a little kind of bump. Oh, and I only want half. I don't want a full oscillation on that one. So the other thing that we probably would want to do is we would want to elide this jump. So the T-bob part we'll probably want to make, if you happen to be landing and you're going to do an immediate jump afterwards, you'd get double oscillation in here. So what we want to do is actually elide that as well if you're going to be doing another jump afterwards. I'm out of time, so we won't try to do that now, but that's basically what we would want to do. So I'm going to see what happens if we speed this back up again. To a faster jump, although I got to put an F in there. I don't know why. I got to figure out why we are able to jump outside of there. I'm not really sure why. We haven't looked at that stuff much yet. But we're getting much closer to a real sort of jump. The speed at which the jump has to happen is a little bit much. And so what I'll probably do too is I'll probably move some of that animation into the actual pre-movement code so that as you move the head, it squishes down, right? So like it gets ready to jump as I kind of move away, and then it jumps. So I may actually not need to do as much windowing there. I may actually move those out into the other state. But I just kind of wanted to show you how to do that to start with. So I'm going to go ahead and go to the Q&A. You know what we should also do? the Cysic, what's the difference between B-splines and Bezier curves? I will draw it here. So to start with, the difference in terms of the curves they produce is there is no difference. So a Bezier curve and a B-spline curve are actually the exact same curve. It's just how the knots are phrased. And I'll sort of, a knot and a control point, you might hear me use kind of interchangeably, and that's because they are interchangeable when you're talking about a B-spline, but they're not as interchangeable when you're talking about Bezier. A knot are like the t values at which your control points occur, and control points are the positions along the curve. So for example, I don't know why I drew these under Bezier. Probably not so smart. So if you imagine, let's say I was going to do a curve kind of like the one I had before. So here are the points that I've specified, and here's the curve that I'm drawing. Okay? So what happens here is these are control points. And maybe I shouldn't, I'll save just explaining knots till after I say the B-spline thing. So if I'm talking about a Bezier curve, then the number of Bezier curves in this example is actually 2. And the number of B-spline curves is only 1. And as I can't get this here. And so what we're talking about when we talk about Bezier curve versus B-spline curve is the fact that a Bezier curve is a fixed curve with a number of points equal to its order plus 1. So if I have a third order Bezier, which is the kind you normally have, and I'll put this in the middle, I guess. If I have a third order Bezier, then the number of points it has, control points, is 4. This one, this one, this one, and this one are the control points of the first Bezier curve. Okay, and this is its arc. Then there's another Bezier curve, which is this one, this one, this one, and this one, right? Which is another 4 points. And this is its arc. What you do with Bezier curves, if you want them to chain together, is you set the control point that's one before, that's like essentially the one they would call the tangent handle. The control point that's one before the point that you end on, you set that to be exactly opposite and the same length away as the first tangent handle in the next Bezier curve you're trying to line up. And you set the final point and the first point of the two curves to be coincident, right? So this is 0, 1, 2, 3 of this first curve, and it's also 0, 1, 2, 3 of the second curve. 3 and 0 are the same point here. And furthermore, in order to make this a continuous curve, 2 and 1 in these cases here have to be exactly opposed, right? So to state it mathematically, if this is A, B, C, then what I'm talking about is the fact that A minus B, which is that vector there, has to be exactly equal to C minus B, right? And then another way to state that would obviously be if I wanted to know what this value was here, the C value. It's a wait, did I do that right? I did that wrong. Negative C minus B, right? So it's A minus B equals negative C minus B, right? Because they have to be pointing in the opposite directions of each other. And so A minus B equals negative C plus B, right? Or if I wanted to consolidate and I'm like, I have my A and I want and my B and I want to know what that C value is, right? Then I've got A minus 2B equals negative C, or C equals 2B minus A. Okay? So that's Bezier curves. And so what you're doing with Bezier curves, if you want to make a long curve, you have to keep stacking them on top of each other. Stack, 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 stack. And if you want them to be continuous, which you normally do, you have to always obey this. And so these handles are locked. Now in a drawing program, you've seen this. It's called lock tangent handles. And you can unlock them to make a bend, like a crease in the curve, right? And so what happens when you make a crease in the curve is when you stop obeying that thing. Because at that point, because these are two totally separate curves, they will the second one will start out in a direction that's totally different from the one that the first one ended in, right? And with a third order curve, you can actually have the directions be the same, but the accelerations are different, right? And that's what would happen if I kept these as in line, but I made like this one longer. Right? So this one you would still see a sort of second order. It wouldn't be a perfectly true curve. It wouldn't kink, but it would like, you could see that there was a second order change. All right. So what's a B-spline? That's a Bezier. A B-spline curve is if you pre-solve for this stuff, right? If you just say, I'm always going to be continuous, so I'm just going to say, hey, you know what? I'm going to specify this, 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 and this, right? And I'm going to keep going. And I just want my curves to kind of come all through together. I just want them all to be control points, right? So what you do instead of, in the Bezier case, you end on one of your control points, right? You start on one control point and you end on another control point. In a B-spline curve, that's still true for the very end, but all the rest of the way through, you actually don't ever do that. So you would place your control points and the curve would never quite hit it. So if I actually had the exact same control points, I didn't modify them, right? If I actually fed the exact same control points in and didn't double this one anymore, so this isn't 2 anymore, it's just 1 control point. I start out here and I kind of like pass through these guys, like that kind of a thing, right? If I doubled this guy again, then I would hit him. But you don't want to do that. Actually, is that true? I'm sorry, no, you would not hit him. You'd have to triple him if you actually wanted to hit him, I believe. Because it would be I think you'd have to actually triple him. That's neither here nor there. So what a B-spline does is it basically solves for this a priori and says, I'm going to write the equation of a curve that just continues to flow through its control points without ever touching any of them until the very last one, right? So it's as if you had a B-spline, as if you had a Bezier curve that lasted for many, 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 many control points. And the way that they do that is just by pre-solving these equations to essentially turn around the phrasing of the curve, so that you're sort of saying, well, when I'm between this curve, when I'm evaluating t between here and here, right? What I'm actually going to do is evaluate this Bezier, effectively. When I'm between here and here, I'm going to evaluate this Bezier. So I switched up which points I was doing. Before I finished actually even tracing out what the first Bezier would have been, I'm shifting to the next Bezier, and then the next one, and the next one, right? So a B-spline constantly moves the frame forward through time to avoid you ever getting to the end until you get to the last knot. They're exactly the same curve equations, though. So the kinds of curves you produce with either or are exactly the same, and you can take a Bezier and fit it to a B-spline and fit a B-spline to a Bezier, and they will be exact. So there isn't any difference in the actual curve. The only difference is how you are actually controlling that curve. What the control points actually mean and which ones you specify is what changes. So if I have a B-spline that looks like this, I have a Bezier that looks like this, they, the same control points fed into both of them won't produce the same curves. But there is a set of control points that I could feed into one that would produce the same curve as some other set of control points in another. If that makes sense. From a beginner's perspective, it seems that in software rendering, keeping milliseconds per frame in a certain controlled boundary is somewhat in the programmer's control, depending on the code quality and orientation toward performance. Does that become more difficult when going to hardware rendering with drivers territory, or is it the other way around? I would say it's actually hard in both, because in one case you don't know what CPU you're running on, and that's kind of a little bit difficult. But in the other case, you don't know what GPU you're running on, and so it's the same difficulty. In both cases, it's really hard on a PC. That's why people oftentimes enjoy programming on consoles, is because it's one piece of hardware, so you do have a lot of control. You're like, we know that if we do these things, it will work, right? We don't have to wonder about what will happen on this GPU or that GPU or this CPU or that CPU. Dude in Basement 1, are we going to do any compression on the image or only movement of the torso? We're going to have to stretch the cape to reach the head. So that's going to have to happen. FSJS. I don't really discuss game design stuff on the stream, so I'm gonna skip that one. Is it possible to create animations like Looney Tunes where looking at still frames you could see multiple heads and limbs or features that are extremely exaggerated and distorted somehow? It still looks fine in motion. Smear animation is a term I could find in 30 seconds of Googling. I'm not sure exactly what you're asking about. You're talking about just like multiple static frames? And the answer is yes, you can totally do that. Looks like we're out of cues. Yes, we're out of cues, except for let's see here. Why not use Java instead of C? I feel like I've covered this lots and lots of times. So I guess my sort of base question would be, name the professional 3D game engines, or really name any professional engine written in Java. And the answer is there aren't any, right? Frostbite, not Java. Unreal, not Java. Unity, not Java. Destiny's engine, not Java. And so if you want to program in games and you're trying to get a job programming games and the only thing you know how to program is Java, you're not going to get a job on an engine team. If you want to program little toy games or whatever, and that's, you're happy doing that, or you just, don't care about, sort of advanced game engine programming, then that's fine. You can use any language you want, right? Because it doesn't matter. You could use Python. You could use PHP if you wanted to, right? But the answer is high-end game engine programming is never done in Java, ever, under any circumstances. Most games aren't written in Java either, even if they're not high-end. So, there's Minecraft, whose performance is abhorrent, even though they're not even doing anything in the game, is written in Java, but at least I guess it works. But that's like one of the only games you can even think of that's written in it. So even most time people don't. Like, if a lot of games are written in C# nowadays, because like there's the XNA framework, and Unity obviously is also kind of like has C# on top of it. So that's kind of more of if you were going to program in Java, I don't know why you would ever actually program a game in Java, because it seems like C# is more the kind of supported platform for gaming. You have a lot of choices for engine stuff and whatever, whereas Java, you've really got nothing that I know of. unless, maybe it's like a mobile game on Android or something, since that's kind of a Java-y platform. But so all of that is whatever, do whatever you want to do. But as far as like why we don't use Java in the stream, it's because this stream is for people to learn how to be game engine programmers, and there are no game engine programmers who, like, there are no game engines that get written in Java. So, it would be useless for me to teach. Nobody wants that. No one's going to hire you, right? JMonkey and LWJGL are professional open source libraries written in Java. Just to name a couple. No, engines meaning game engines. Those aren't game engines that anyone actually uses. Like, what game can you buy? Name any game on the Steam, like, that's been in the Steam top 50, right? Its engine is not Java, right? Where will you go to work? At which game company do you believe you would be working on an engine that's written in Java? There aren't any. It just doesn't happen. It's like, it'd be like Zynga or something would be where you would be working if you're talking about Java game engines. They're like these little toy things. They're not the serious, they're just not the serious engine. And maybe you could, again, C# is kind of one of those things that's a little more relevant because a lot of those work, but in a lot of those work in in the Unity pipeline, or some people write games in XNA. Like I think like Bastion was written in XNA, and Fez. Probably time to just take questions from the Handmade Network IRC. Yeah, I don't actually know how to get on that IRC yet. I should. In order to stretch the body to the head, will we be implement shearing? Probably not shearing. I don't know. We could, but I think shearing would be rough. What would your ideal game programming language look like? It'd be very meta-programming oriented. Have you seen this video on Ubi's Rayman 2D animation editor? No, I haven't. But I would like to. Oh my god, there is a wall of buttons. I'll have to look at that later. It looks pretty involved. So I asked the kid, will the animation function eventually be moved out so other entities can use them? Yeah. Gasto05, is it recommendable to mix vector and raster graphics for a game? I would say that, it depends on the circumstances. There's certainly no reason you can't do it. But, whether it's appropriate for your situation is going to depend. David Rosen at Wolfire had a GDC talk on procedural animation. Have you seen it? If so, thoughts? Yes, I have seen it, and I thought it was pretty good. The animation in Overgrowth, though, has some issues to it. So I'm wondering, I felt like it should look better than it did, given sort of the way he was talking about it. I feel like there may be some weirdness. I feel like he's maybe not using, enough, what's the word I'm looking for? I feel like he's maybe not using enough animation for it, if that makes sense. He's not using enough sampling, would probably be my my guess. So what he should probably do is work more with the velocities, I think, is the problem. Because I don't know. I feel like the techniques he was describing, I feel like they would work really well, but when I looked at the animation, there's a lot of discontinuity in the second derivative to it. So I just feel like there's some implementation problems, because I feel like the techniques should have worked better than what they end up looking like. That's I don't know. So I'm not sure. But that said, it's not shipped. The game's not out, so I don't maybe they know all about that and they're like, yeah, we haven't finished, this sort of thing. How close is humanity to programming a facsimile of our universe? How should I know? What do you have to say about the researchers that claim that Java can be faster than C++ at times? I have looked at every single time people have claimed that, and I was like, yep, they're wrong. I went and looked, and I was like, here's how they did it, and I was like, nope, that was just stupid. Because it can't be. I mean, it's kind of ludicrous to even think that it can be. Because it doesn't really make any sense. And you go to see these researchers and they're hilarious, how bad the paper is. And usually they don't actually mean that it's faster than C++. What they mean is that, if you were to create a certain program this specific way, and you use the Java's construct for it versus the C++'s construct for this specific thing, then it's faster. And I'm like, okay, I don't understand why that's relevant, because I could have done exactly that thing in actual C++ myself if I'd wanted to. So it's not particularly relevant. Now, there might be some things too where, a Java's maybe compiler got optimized for something and, you can't, maybe there's some bad part of LLVM, that you can say, well, okay, this is slower or something like that. And Sean, no, I have not seen. I have not seen. Oh, our fellow Java aficionado here has said that RuneScape, which I don't think I've ever seen, is written in Java. What is RuneScape? It's some kind of an RPG, I guess. I don't actually know RuneScape. Is a graphical browser game on the client side in Java. Okay, that sounds fantastic. Well, if that's the kind of thing you want to work on, go nuts, man. Again, not really a serious game, but okay. They released a C++ client last week. Oh, that's great. Sorry, YOLO swags. The game you cited actually had to replace their crappy Java thing, so bummer, man. I guess you can't work there, but don't worry, there'll still be a job for you at, I don't know, at IBM, integrating parking ticket software for the city of, you know, Pawnee. And I don't think that Minecraft has been ported to C++ yet, has it? Someone was suggesting that it has, but I doubted it. Maybe Microsoft did, I don't know. But you'd think that would have been announced at some point. Oh, the Win 10 edition is okay. So basically, all of the games that were in Java have been rewritten in C++. Is that basically what we're saying? Minecraft got re-released in C++, and RuneScape got released in C++. All right, so I am going to wrap it up since there are no more cues that look relevant. Yeah, and I don't really understand why people ever even talk about Java for programming games, because like almost no games are written in it, and certainly none that are like technically impressive, right? That never has happened, pretty much ever. And it seems like if you wanted that kind of a managed language that's like kind of high level, it does seem kind of like you would end up, you'd end up doing C# these days, because you're writing a Unity game, or you're using XNA, or who knows what you're using, some of those things. Seems like I've seen a lot more. I can think of a lot more games that are that than are Java. Like there's almost none. It's really, 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 really rare. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along at home, you, of course, can. You can pre-order the game on handmadehero.org, and it comes with the source code so you can play around with it at home. You can also go to the forum site, which now is hosted over on Handmade Network. Oops, I got to refresh my page, though. I updated this link. There we go. You can go over to the forums where you can ask questions and stuff like that if you're trying to follow along with the series and you have questions. We also have a Patreon page you can support the video series, a schedule bot if you want to know when the series is going to be live, and of course we also have our little live button which counts down for you, so if you're curious when the show's going to be on and you want to catch another one, you can do exactly that. Until tomorrow, I will catch you guys on the internet. I believe tomorrow is 5 p.m. Pacific Daylight Time, and we will take a look at how to do a little bit more stuff with the animation in there. Take it easy, everyone.